Hello everyone, I'm Prashant Jayanwar and I will be presenting our paper Learning to Execute Instructions in a Minecraft Dialog. This is work done jointly with Angelina Ryan Chen and Julia Hockenmeyer at the University of Illinois at Urbana-Champaign. We are interested in human-robot collaboration, where robots can, number one, have a dialogue with humans about the physical world, and number two, can execute instructions in the physical world. To make progress towards this goal in an inexpensive way and to simplify experimentation, we use the popular video game Minecraft, which provides a simulated 3D environment for construction and navigation. More specifically, we use the previously proposed Minecraft collaborative building task. It is a two-player game between an architect and a builder, where the architect is shown a target structure and instructs the builder how to build it. The builder has an inventory of 120 colored blocks of 6 different colors, and they can communicate via text interface. The task is complete when the build structure matches the target, modulo translations and rotations. Let us look at an example of how humans perform this task. The architect gives instructions, and the builder moves and executes them. Some instructions can be quite complex and may not be fully specified. So the architect may provide further details in the next turn. Some instructions require a lot of blocks to be placed. Floating structures can also be built by removing supporting blocks. Generally, humans perform this task with high accuracy. We introduced this collaborative building task and a corresponding dataset last year. The Minecraft dialog corpus contains 500 odd human-human dialogues and game logs. In that paper, we also defined an architect utterance generation task and proposed neural baselines for it. In this work, we now focus on the builder. Here you can also see some of the actual structures in our dataset. In this paper, we introduced the builder action prediction task. The task here is to predict the sequence of actions, block placements, or removals that the builder performed at a particular point in a human-human game. So if our input was something like this point in the game, where the architect instructs the builder to build a V-shape, our output should be the action sequence that leads to this structure. So why is this task challenging and interesting? From a situated dialog point of view, understanding instructions in this domain requires dialogue and world context. Architect instructions may not be limited to a single utterance, but can be spread across turns. The builder's perspective is also constantly changing, thus changing the meaning of spatial relations. And so is the environment due to actions taken by the builder. From an action prediction point of view, we have a large action space of 7,000 odd actions. Our domain also allows for floating blocks, which require non-monotonic action sequences, where placement is followed by removal. Furthermore, training sequences in our data can get noisy, as humans are prone to mistakes and misunderstanding. Let us now take a look at the models we developed for this task. Our model is an encoder-decoder network with a GRU backbone. It takes as input the game history as a sequence of tokens, and the world state as a 3D grid. The decoder starts decoding by being fed a special start token, and generates a sequence of actions in a recurrent fashion. The world state is also updated at every time step during this process. Generation continues until we generate the stop token. Let us now take a slightly closer look at our model components. We encode game history as a flash sequence of tokens using a GRU encoder to produce a vector encoding of it. We experiment with 3 different schemes to encode game history. Scheme H1 encodes the architect's last utterance and any following builder utterances. And here is an example. On the left, we can see how much history was encoded under this scheme. On the right, the grid structure is what existed from before, and the 2 red blocks are the actions to be predicted. The architect intends to replicate on the other side of the tower the 2 grayed out floating blocks on its right. But as we can see, just the last architect utterance may not be enough context to understand what is to be done here. We may need to refer back to previous utterances as well as previous builder actions. In scheme H2, we try to alleviate this problem a bit by encoding all utterances after the builder's penultimate action sequence. We see that we now have some more context by adding in the utterance in red to that game history. We take this further in scheme H3, which basically interleaves the utterances of H2 with a token representation of the builder's last action sequence. The history now is far more informative. It tells us more about what needs to be replicated when the architect says, and the same thing on the other side. Moving on to the world state encoder. This is a 3D CNN-based encoder that encodes the world state at each time step of the decoding process. It takes as input the 11 by 9 by 11 3D grid, where every grid cell is represented as a 7-dimensional one-hot vector of its block color, including an element in there for the case when the cell is empty. We enrich the world state representation further by encoding history of past actions taken. The key observation here is that actions that follow each other often affect adjacent grid cells, and this motivates the need to encode information about the most recent builder actions. We do so by assigning weights to actions in the action history, such that the last 5 actions get weights from 1 through 5, from the least to the most recent, and all others are weighted 0. And every cell gets the weight alpha of the last action that happened there. We simply concatenate this extra feature to the cell's vector representation. Additionally, we encode the builder's perspective, that is, the builder's position and orientation. This is motivated by the observation that spatial relations in instructions like left, right, etc. often depend on the builder's current perspective. We thus need to be able to represent the world from the builder's point of view. We do so by computing perspective coordinates for every cell. Intuitively, this is equivalent to centering the origin of the builder's position and aligning the axes according to the builder's orientation. So given a cell and its absolute coordinates, we compute its relative coordinates with respect to the builder's current XYZ position and orientation in terms of pitch and yaw angles. We then simply concatenate them as extra features to the cell's vector representation. The action sequence decoder predicts a single action per time step. It consists of a GRU backbone conditioned on the game history. The input to the GRU is an 11-dimensional vector of the action taken at the last time step. The vector encodes the action type, placement or removal, block color, and the absolute XYZ coordinates of the cell where the action took place. A CNN-based action predictor is conditioned on this context as well as the world state at that time. Stop token predictor, conditioned on the action predictor context, generates a score for the stop token that signals the end of the sequence. The final prediction concatenates outputs of these two modules, followed by a softmax to produce a distribution over all possible actions in the grid and the stop action. This concludes the overview of our models. Although our dataset is relatively small, we can perform the following transformations to augment our training data. First, we can permute colors in the world and in the dialog. For example, here blue has become orange, red has become purple, etc. Then we can also rotate the build structure. We do the same for the builder in order to preserve relative spatial relations between the builder and the structure. And we can replace words and phrases with synonyms. We evaluate our systems automatically using an F1 score over net actions. Net actions ignore the order of actions. They also ignore blocks that were placed and removed in the same sequence. Specifically, computer micro averaged F1 over net actions in the ground truth sequence and the model's predicted sequence. We train our models on 3700 training examples, using cross-entropy loss and generate sequences using greedy decoding. Let us now take a look at our model's performance. The rows correspond to various world state representations and the columns to the various game history schemes. Our most basic model in the red cell achieves an F1 of 11.8, whereas the best one in green achieves 19.7. In general, our richer game history schemes work better with H3 being better than H2, which is in turn better than H1. We only consider H3 when training models on augmented data. By augmenting the data to 4x its original size, our performance goes up to 21.2 as shown in green. And we also see that perspective coordinates help once we use data augmentation. Our best model thus uses our richest world state and game history representations as well as data augmentation. Now let us look at some examples of what our best model does. Here is the initial structure. And this was the preceding dialog. The builder had just placed the 2 blocks atop the ends of the row of 3 blocks to create a U. Now let us look at what the model does. The model can indeed interpret, do it one more time, and extends the U upwards by placing 2 more blocks. This is consistent with what the human builder did. This example is more complex. Over the course of some back and forth dialogue with the architect, the builder has just built the leftmost 2 yellow blocks of the left yellow row. Now let us look at what the model does. Our model interprets do the same on the other side as placing another 2 yellow blocks, but places them in the wrong location. Whereas the human builder is able to understand that the architect needs to place the blocks on the other end of the row in progress. Now let's look at this example. After the builder places the rightmost purple block, the architect directs the builder to place another red block on top of it. The model seems to interpret this instruction correctly. But due to earlier parts of the conversation, the human anticipates the next actions and adds the second red block and removes the purple blocks. This indicates that automatic evaluation against human action sequences may be overly harsh. Our qualitative analysis clearly shows that our model understands more than these metrics may suggest. In summary, in this work, we have defined a new challenge for situated dialogue, namely the builder action prediction in Minecraft. We have developed models that process the game history, along with 3D representations of the evolving world to predict action sequences. We have also showed that our approaches to modeling and data augmentation improve over naive baselines. And as for future work, we intend to focus on better understanding of spatial relations and game context, as well as explore better ways to evaluate models. Our data and code can be found at the link at the bottom. Thank you.